In the first decades of the 20th century, physicists opened a strange window into the heart of matter. Radioactive atoms, they discovered, could transform themselves. In one process, called beta decay, an atomic nucleus spat out a fast-moving electron and became a different element altogether. A carbon nucleus might shift toward nitrogen. A heavy element might inch closer to stability. It seemed, at first, wonderfully simple. The physics of the day made a clean prediction. If a nucleus began at one fixed energy and ended at another fixed energy, then the electron flung out in between should always carry the same precise amount of energy. The difference between the starting state and the finished state was a single definite number. Every emitted electron should have arrived at the detector with that exact energy, like coins stamped from one mold. But nature refused to cooperate. When experimenters carefully measured the electrons streaming from beta decay, they found no single value at all. Instead, the electrons emerged with a whole range of energies, spread across a smooth, continuous band, from nearly zero up to a sharp maximum. Some electrons carried almost the full expected energy. Most carried far less. The numbers simply did not add up. Consider what that meant. The atom lost a fixed quantity of energy in the transition, yet the electron that carried it away often held only a fraction of that amount. Where had the rest gone? It was not absorbed by the apparatus. It was not radiated as light anyone could catch. It appeared, measurement after measurement, to have simply ceased to exist. This was not a rounding error or a faulty instrument. The pattern repeated in laboratory after laboratory, with different elements and different techniques. The missing energy was real, reliable, and deeply unsettling. To a physicist, energy is not supposed to leak out of the universe. It is supposed to be counted, tracked, and conserved down to the last decimal. And here was a common natural process seeming to swallow energy whole. A crisis was quietly taking shape, one that would soon threaten a principle scientists had trusted for over half a century. To understand the alarm, you have to understand what was at stake. The conservation of energy was not one rule among many. It was bedrock. Since the mid-19th century, the principle had held that energy can change form, but can never be created or destroyed. Heat becomes motion, motion becomes electricity, chemical bonds release light, and through every transformation the total remains fixed. Engineers built machines on it. Chemists balanced reactions with it. Astronomers traced the lives of stars by it. It was, in a real sense, the accounting system of the entire physical world. And now beta decay seemed to be cooking the books. The evidence grew sharper through the 1920s. James Chadwick, working in the Cavendish laboratory, had already in 1914 measured the energies of beta electrons with real care. His results showed not a single spike, but a continuous spectrum, a smooth curve of energies from low to high. For years, some physicists hoped this was an artifact, that the electrons had lost energy on the way out, bumping through the atom or the surrounding material. But refined experiments closed that escape route. In 1927, Charles Ellis and William Worcester performed a decisive measurement. They placed a beta-emitting source inside a thick-walled calorimeter and measured the total heat released. If electrons secretly began with the full energy and lost some along the way, the calorimeter should capture that maximum energy as heat. It did not. The heat matched the average energy of the electrons, not the maximum. The missing energy was genuinely gone before the electron ever reached the wall. This was damning. The anomaly could no longer be blamed on sloppy technique or hidden absorption. Nature itself, in the quiet decay of a nucleus, seemed to be violating the most trusted law in all of physics. Physicists faced an impossible fork in the road. Either the sacred principle of energy conservation had a limit, breaking down somewhere inside the atom, or something invisible was slipping past every instrument, carrying the balance away unseen. The debate that followed would draw in the greatest minds of the age, and one of them was ready to abandon the law entirely. That mind belonged to Niels Bohr, From his institute in Copenhagen, Bohr had already reshaped physics once, giving the world a new picture of the atom with electrons in fixed orbits. He was not a man frightened by strange ideas, and by the late 1920s he had come to believe that beta decay might be pointing towards something genuinely revolutionary. His proposal was as bold as it was disturbing. Perhaps, Bohr suggested, energy conservation was not an absolute law at all. Perhaps it held only on average, only across many events, while in any single beta decay, energy could quietly be lost or gained. On the vast scale of ordinary machines and stars, the fluctuations would cancel out, and the law would appear perfect. But down in the subatomic world, in the intimate act of one nucleus decaying, the ledger simply might not balance. To most physicists, this was almost heresy. Yet Bohr had reasons for his daring. The quantum world was already proving to be a place of deep strangeness, where certainties dissolved into probabilities and old rules bent in unfamiliar ways. If nature could be that odd, why should the conservation of energy be untouchable? He even hoped the idea might solve other puzzles, including questions about the strange behavior of energy inside stars. The crisis split the community. Some sympathized with Bohr, willing to follow the evidence wherever it led, even off the edge of a cherished principle. Others recoiled. To surrender energy conservation felt like pulling out the foundation stone of the entire building. If that law could fail, what could be trusted at all? Physics threatened to fracture between those who would rewrite its deepest rule and those who refused. The stakes could hardly have been higher. On one side stood the most successful principle in the history of science. On the other stood a small anomaly in the decay of atoms, insisting that something was wrong. Someone needed a way out that saved the law without ignoring the data. That someone would not abandon conservation. Instead, he would gamble on an invisible ghost that no one had ever seen. The gambler was Wolfgang Pauli, a physicist famous for his sharp mind and sharper tongue. Where Bohr was willing to let the law fall, Pauli was not. He believed energy conservation was worth defending, even at the cost of proposing something almost embarrassing. On the 4th of December, 1930, he set down his idea, not in a formal paper, but in a letter. He addressed it playfully to a gathering of physicists in Tübingen, opening with the words, "Dear radioactive ladies and gentlemen." He could not attend the meeting in person. He had, he joked, a dance to go to. But the proposal inside was serious. Pauli suggested that the missing energy was not vanishing at all. It was being carried off by a new, undetected particle emitted alongside the electron in every beta decay. This particle would be electrically neutral, so it left no trail of charge. It would be extraordinarily light, perhaps massless. And crucially, it would share the energy of the decay with the electron. Sometimes the electron took more, sometimes the particle took more, which explained the continuous spectrum perfectly. On average, nothing was lost. The law was saved. But Pauli knew the cost of his own idea. To make the energy books balance, his particle had to interact with matter so feebly that it could slip through solid walls, through the entire Earth, without leaving a mark. And that raised a terrible worry. He confessed it plainly. He had done a terrible thing, he said, by proposing a particle that could never be detected. A theorist should not invent something that experiment could never test. It felt almost like cheating. He first called it the neutron, borrowing a name that would soon be claimed by a different, heavier particle discovered in 1932. Pauli's ghost was something else, far fainter and far stranger. So there it stood, a rescue built on faith. A particle nobody had seen, defined mostly by its refusal to be seen, holding the law of energy conservation together by sheer theoretical necessity. It needed more than a letter to survive. It needed a theory, and it needed a name. The man who gave it both was Enrico Fermi. Working in Rome, Fermi possessed a rare gift, the ability to move fluidly between deep theory and hard experiment. Where Pauli had offered a rescue in a letter, Fermi would build a complete mathematical machine around the idea. In 1933 and 1934, he constructed a full theory of beta decay. In Fermi's picture, the process was not a particle simply leaking out of the nucleus. Instead, at the moment of decay, a neutron inside the nucleus transformed into a proton, and in that same instant, two new particles were created and flung out together. The electron everyone could measure, and Pauli's ghostly neutral particle. The energy of the decay was shared between them in every possible proportion. From this, Fermi's equations produced the exact shape of the continuous energy spectrum that experimenters had measured. The theory did not just explain the missing energy. It predicted in precise detail how many electrons should emerge at each energy, and the prediction matched the data. It was a triumph of reasoning, turning a desperate guess into rigorous physics. Fermi also gave the particle its lasting name. Since Chadwick had by then claimed the word neutron for a heavier, well-behaved particle, Fermi coined a new term in Italian, neutrino, meaning little neutral one. It was tender and precise, a name for something tiny, uncharged, and elusive. So light, so faint, it was almost nothing at all. There was a striking irony in the theory's reception. Fermi submitted his work to a leading scientific journal, and it was rejected, reportedly as too speculative, too far from physical reality. One of the most important papers of the century was turned away for reaching too boldly. Yet the framework endured. With Fermi's mathematics, the neutrino was no longer merely a clever escape hatch. It was woven into the structure of a working theory, a particle with defined properties and testable consequences. The law of energy conservation stood intact, propped up by an invisible entity that now had equations, a name, and a role. But it still had no proof. The neutrino remained a creature of paper, and catching it would seem, for years, utterly impossible. By 1934, Enrico Fermi had given the neutrino a name and a role in his elegant theory of beta decay. But naming a ghost is not the same as catching one. The very property that made the neutrino useful made it maddening. It carried energy away precisely because it barely touched anything. Fermi's own equations hinted at the scale of the problem. A neutrino could slip through the entire Earth as though the planet were empty space. Calculations suggested that to stop a single neutrino reliably, you might need a wall of lead measured not in meters but in light years. The particle interacted only through the weak nuclear force, the faintest of nature's four fundamental interactions. In 1934, physicists Hans Bethe and Rudolf Peierls worked out the odds and concluded there was no practical way to observe one. They wrote that the neutrino could never be detected. It was a strange verdict, a particle demanded by the sacred law of energy conservation, endorsed by Pauli and formalized by Fermi, yet apparently beyond the reach of any conceivable experiment. For nearly 2 decades, the neutrino lived a paradoxical life. It appeared in equations, balanced the energy books in beta decay, and explained the continuous electron spectrum that had haunted physics since Chadwick's measurements. It worked flawlessly on paper, yet no instrument had ever registered its passage. Trillions of neutrinos streamed from the sun through every human body each second. Unfelt, unseen, unrecorded, physicists began to accept an uncomfortable truth. They believed in something they might never confirm. The neutrino became the perfect test of scientific faith, a prediction so confident and so useless at the same time. To catch even a handful, you would need an enormous, relentless source pouring out neutrinos in unimaginable numbers, and a detector clever enough to register the vanishingly rare collision. In the early 1950s, the world had finally built machines capable of producing such floods of particles. Nuclear reactors, born of wartime physics, released neutrinos by the trillions upon trillions. 2 American physicists looked at those reactors and asked a question no one had dared to answer. What if the impossible could be attempted after all? Their names were Clyde Cowan and Frederick Reynes, 2 physicists at Los Alamos with a taste for audacious problems. Around 1951, Raines became obsessed with an idea most colleagues considered hopeless, actually detecting the neutrino. He recruited Cowan, and together they gave their experiment a fittingly eerie name, Project Poltergeist, after the ghost they hoped to trap. Their first wild scheme was to place a detector near a nuclear bomb test, using the immense burst of neutrinos from the explosion. They soon realized a nuclear reactor offered a steadier, safer flood, hundreds of trillions of neutrinos per square centimeter every second. The genius lay in the detection strategy. Fermi's theory predicted a specific reaction. An antineutrino striking a proton would produce a neutron and a positron, a process called inverse beta decay. Cowan and Raines designed tanks filled with hundreds of liters of water, laced with cadmium chloride. When a rare neutrino struck a proton, the positron would instantly annihilate with an electron, releasing 2 flashes of gamma light. Microseconds later, the neutron would be captured by a cadmium nucleus, producing a second telltale flash. That precise double signature, 2 coincident pulses separated by a tiny delay, would be nearly impossible for anything else to fake. Surrounding the water tanks were racks of photomultiplier tubes, sensitive enough to catch the faint bursts of light. The whole apparatus, weighing tons, had to be shielded from cosmic rays and reactor radiation that could drown the delicate signal in noise. In 1953, they ran an early version at the Hanford reactor in Washington. The results were tantalizing but ambiguous, buried in background interference. Undeterred, they refined everything: larger tanks, better shielding, sharper timing electronics. They moved their equipment to the powerful Savannah River nuclear plant in South Carolina, burying the detector deep beneath the reactor to block stray radiation. There, in the humming dark, tanks of water waited for a particle that Bethe and Peierls had once declared undetectable. Every recorded coincidence was scrutinized, every false signal ruthlessly eliminated. For months the team watched their instruments, hunting for the double flash that would prove a ghost had finally struck. In the spring of 1956, the signals began to accumulate at Savannah River. Deep beneath the reactor, Cowan and Raines watched the delayed double flashes appear exactly as Fermi's theory predicted, the positron annihilation. Then microseconds later, the cadmium capture. They ran control tests, switching the reactor on and off. When the reactor operated, the events climbed. When it shut down, they fell away. The correlation was undeniable. The signal rose and vanished in step with the neutrino flux. After painstaking analysis, they measured a detection rate of roughly 3 events per hour, matching prediction. The impossible experiment had worked. On June 14, 1956, they sent a telegram to the one man who deserved to know first. Wolfgang Pauli, now at Zurich, received the message. Their apparatus had definitely detected neutrinos from fission fragments, confirming the particle he had proposed 26 years earlier in a letter he once feared no experiment could ever verify. Pauli reportedly interrupted a conference to read it aloud, then celebrated with champagne. The ghost he had invented out of desperation in 1930, the neutral particle he doubted could ever be seen, was now real, measured in tanks of water in South Carolina. Pauli sent a reply, gracious and relieved. He wrote that everything comes to him who knows how to wait. Decades of theoretical faith had finally met experimental proof. The particle that Bethe and Peierls declared undetectable had been caught, not by a light year of lead, but by clever chemistry, precise timing, and a torrent of reactor antineutrinos. The continuous electron spectrum that Chadwick had measured, the missing energy that once threatened the foundations of physics, the desperate remedy Pauli proposed and Fermi formalized, all of it was vindicated in a single confirmed rate of events. In 1995, decades later, Frederick Raines received the Nobel Prize for the discovery. Cowan had died in 1974 and could not share it. But in that June telegram of 1956, physics recorded a triumph larger than any single career. A prediction made in the dark had become a signal in the light. And with it, a law once teetering on the edge of collapse stood firm once more. Consider what had truly been at stake. In the 1920s, beta decay's continuous energy spectrum seemed to show energy simply disappearing. Niels Bohr was prepared to abandon energy conservation itself, to declare that on the atomic scale, one of physics, deepest laws might not hold. Wolfgang Pauli made the opposite wager. Rather than sacrifice the law, he invented a particle to defend it. An unseen, nearly massless, electrically neutral messenger carrying off the missing energy. The 1956 detection proved him right and Bohr wrong. Energy conservation survived intact, rescued not by retreat but by imagination. Yet the neutrino gave physics far more than a saved law. Confirming it opened an entirely new frontier. Fermi's theory of the weak interaction, built to explain beta decay, became a cornerstone of what would grow into the standard model of particle physics. Physicists soon discovered that neutrinos come in different types, electron, muon, and tau, and that they can transform from one type into another, oscillating as they travel. That discovery, decades after Savannah River, revealed that neutrinos possess a tiny mass, something Pauli never anticipated. Neutrinos now serve as astronomical messengers. They pour from the sun's core, from exploding supernovae, from the earliest moments of the universe. Enormous detectors buried in mines and Antarctic ice catch them, letting us peer into places light itself cannot escape. The ghost particle became a tool for seeing the invisible interiors of stars. The story endures because of what it reveals about science itself. Faced with a crisis, physicists trusted a law so deeply they were willing to conjure an undetectable particle to preserve it, and then spent 26 years proving that conjured particle was real. Pauli's leap of faith, Fermi's mathematics, Cowan and Raynaud's tanks of water, all bound together by a single conviction that the universe keeps its books balanced. From a puzzle of vanishing energy to a triumphant telegram in 1956, the neutrino transformed physics forever. It began as a desperate guess and became one of the most abundant particles in the cosmos. This is the story of a law saved by an invisible particle.